2017.
Hello, my name is Igor, and here with me is Linar and Yaroslav. Our team does decompilation and deobfuscation and has experience with most of the common architectures. We also do code analysis, source and binary, including pen testing, manual static analysis, and we also develop analysis tools. In today's talk, we would like to tell you about one of our analysis tools. So we were doing quite a lot of manual iOS security analysis, and a significant part of the analysis process was the same from application to application. So we decided to write a tool that will do most of the work for us. Our goal was to develop a tool that would take an iTunes application link as an input and give us a security report and a record code as an output. So here's our plan. First, we would like to obtain an application binary. Then we'll translate this binary into some internal representation, analyze this representation for security flows, and then translate it into human-readable pseudocode. This last step is important because we want to show each vulnerability in some human-readable context. Okay, and the first part is how to get a binary. So getting an application binary is not as trivial as it may seem, because all iOS apps are distributed through Apple AppStore only, and the binaries in the App Store are decrypted. Moreover, the only known way to decrypt an App Store application binary is to start the application on an iOS device, let device's processor decrypt it and load it into memory, and then dump that decrypted binary from memory. To make this work, we will need a jailbroken iOS device. And as we anyway need a jailbroken device to decrypt the application, we can use it to download the application as well. So this whole step, getting binary, will be done on the jailbroken iOS device. So let's quickly overview what we can do on a jailbroken iOS device. Of course, none of this is available on a stock iOS device without jailbreak. First of all, we can connect to the device using SSH protocol and get a nice bash command line. What is more, there is a code injection platform called CD Substrate, and it provides an API to call any method from runtime of any running iOS application, and also allows us to hook any such method and change its implementation. And finally, there's Clutch, out-of-the-box tool to decrypt and dump iOS applications. So we decided to go with the highest level possible and just use graphical interface when convenient. That means that now we need to first figure out a chain of method calls and GUI decisions to initiate and manage and load, and then figure out how to make needed GUI decisions programmatically. So in order to do that, we need to work with two built-in iOS applications, Springboard app and AppStore app. Springboard is a central application in the iOS graphical interface. So we needed its runtime to make our GUI decisions, like dealing with some system alerts and stuff. We also need to use AppStore runtime to initiate download. So we figured out this stuff and home to this chain of method calls. First of all, our tool unlocks device. Then it uninstalls all apps to make space. and then opens an iTunes page like this one with target application. Then at this page we need to press this get button. After that, AppStore will ask us to sign in, and there will be some alert, and we need to fill our login and password and press OK. Then the download will start, and we will wait until this get button become open button, meaning that the application was downloaded, and that we can come to the final step and decrypt it with Clutch. So now let me just show you how it's done. Okay, it's So here I have an iPhone, this one, and the screen shows here. So I'm going to launch my script and see what happens. Now we need to wait a little bit. And that's it. Okay, and now it's completed. So that's how it works. Okay, and next part is what we do after that. We are going to translate decrypted binary into intermediate representation.
So, as soon as we get a decrypted binary, we need to translate it into the intermediate representation that is suitable for analysis and representing results of vulnerability search. As most translation tools, compilers as well as decompilers, we decided to use an intermediate representation that is more high level than the binary code, but more low level than source code. To obtain precise results, we have to deal with the following challenges during binary translation. In particular, we have got a lot of things to recover. First of all, we need to separate functions from the data and attach names to these functions with correspondence to the function names from the source code, if it's possible, of course. For example, if the source code contains a function that disables certificate checks, we have to know its name to understand the source code semantics. Otherwise, it will be very difficult to us or even impossible to find vulnerabilities in such code. Moreover, we have to understand what arguments are passed to the function, and also we should know the values and types. Based on that information, we have to recover the original semantics of the program inside the IR, including control flow graph of the program and the flow of the program. The majority of the source code is written in Objective-C or Swift, so we have to recover runtime information interfaces from the binary file. That is classes, interfaces, protocols, and other stuff. Applications are mostly fat binaries that contain at least 2 executable images for the ARM architecture and for the RR64 architecture. At first, we supported translation for both ARM and RH64 architecture, but now, as developers and mobile platform owners are mostly focusing on the RH64 architecture, we have abandoned the ARM architecture support and do not support it anymore. Well, as I said before, we had to pick some intermediate representation that is suitable for representing binary program semantics and suitable for security analysis. So we decided to use the LVM as internal representation of recovered code. LVM provides a handy static single segment based intermediate representation that is well suited for representing C family programs, including Objective-C programs and even Swift. Moreover, we can run multiple analyses built in VM for program transformations and optimization, including the alias analysis, many of them, dominators, tree builders, loops analysis, and other transformations and optimizations. Also, we have much experience with this representation, so LVM was the perfect match for us. There are basic ideas that we implement in our translator. We implemented a high-performance tool that translates iOS applications to LVM. It can recover functions and function calls, arguments of that functions, and function types, recover control flow graph of the program, and reconstruct types and variables. During the translation and analysis, we also use all information about classes and interfaces we were able to recover. And this is the basic picture how it works. Our tool receives a binary application as input, passes the image and creates an application memory model. Based on this memory model, we can extract information about classes, about functions, and recover the control flow graph of the application. We analyze this data using various algorithms based on the information we recovered before and based on the data flow of the program. So this is how we recover variables and even the types. After that, we generate the LVM representation and optimize it for better results. During the image passing phase, the encrypted binary, the decrypted binary is unpacked if necessary. The file format that is used for executable in iOS is called Mako. The Mako binary format was well documented until Apple removed the documentation from the public access. Using self-written Mako parsers, we extract information about program symbols and pass runtime information, as well as information on classes and interfaces of the application for both Objective-C and Swift. Once we pass the image, we start the process of recovering functions and the control flow graph of the program. For this purpose, we developed an iterative recursive algorithm that takes a work list with addresses of function stars as input. We use the following sources of function star addresses. There are entry point, address from the function stars section, function addresses obtained during runtime parsing. For example, function addresses from the Objective-C class definitions or virtual functions addresses from Swift or C++ virtual tables. The algorithm recursively traverses all the functions at known addresses and creates a control flow graph for each recovered function. We also have to take special care of trampolines and tail calls. Here you can see an example of trampoline for function of C release. During the translation, we replace this trampoline with a call to the real OPC release. Functions in ARM often end with a tail call, which also should be accounted for in the CFG recovery. This is an example of an idiomatic code for the iOS application. A function concludes with the tail call to the Objective-C release. So we should take special care about it. As I mentioned earlier, we recover the information on interfaces of Objective-C and Swift classes. In particular, we're able to recover classes, protocols, method names, signatures for Objective-C classes. For Swift, we can only recover the class hierarchy and create virtual tables for these classes. All our information on Swift classes is lost during compilation, so we are unable to recover it. We also implemented our own debugger for Swift symbol names to make translation results more human readable. So there is an example of recovered Objective-C interface, and there is an example of recovered auxiliary information about an Objective-C class. There is an encoded signature for each method of the class. We can decode the signature to get precise information about argument types and the region time type of this function. Next slide shows us an example of recovered Swift class. It's worth mentioning that we were unable to recover anything but class names and virtual tables. Even function names are missing and cannot be recovered from the binary. So, after we obtain the basic information about the functions, we run a series of analyses to get more precise information about the semantics of the program. During analysis, we recover the memory objects used by the program, such as temporary variables, local and global variables, and most importantly for security analysis, strings. We also recover types of variables and arguments. In our current implementation, we only support integer, float, and pointer types, but we are currently implementing the recovery of complex types such as arrays and structs that has been already implemented in an other hour in binary to LLVM translation tool for ENTL architectures. We can get more precise results using the knowledge base of known function signatures. For example, standard library or widely used libraries like OpenSSL and others. Moreover, the function signature information for Objective-C methods is encoded in the binary, so it can be recovered and propagated during type recovery. Based on the obtained information, we generate an intermediate representation that preserves the semantics of a given program. The obtained model is optimized for further analysis. For example, we remove jailed code and run constant propagation paths, which is very useful when analyzing the function arguments. So let's see an example of ARM to LLVM translation. This slide contains an example of an Objective-C function. It's actually a part of the function in a binary application. And this is how this function was translated to the LLVM. So, as you can see, we recovered names of called functions and precise argument types. And finally, this slide contains the control flow graph of the recovered function. So this is how binary recovery and translation is done by our translation tool.
So We have LLVM bytecode, and we want to find vulnerabilities in it. At first, we decided that it would be better if we show our detected vulnerabilities in some human-readable context. So we developed a tool that recovers some Objective-C Swift-like pseudocode from LLVM bytecode. The ultimate goal of this work is to develop the compiler. But for now, we are extracting all the information we can get from binary code. Function names, signatures, call sites, arguments, types, statements, etc. We are improving structural analysis, which includes precise recovery of loops and if-else statements. It will make this tool much closer to the compiler. In Swift binary code, we have less information than in Objective-C binary code. For example, we have no function names. So Objective-C recovery is more accurately. But in most cases, there is enough information for interpret the detected vulnerabilities. When the application uses Swift, its binary contains both Objective-C and Swift functions, and during the binary translation, we determine which function is written on what language, and we propagate this flag to the pseudocode. So depending on this flag, we use Objective-C or Swift parity printing. Our research shows that the most dangerous vulnerabilities can be usually found by pattern matching. Also, pattern matching is fast, so it is important for large binaries. So we use pattern matching on LLVM for now. For other vulnerabilities, we will develop other data flow analysis algorithms, for example, taint analysis. We have done it already for x86 architecture for detecting memory management bugs and format string vulnerabilities. We find vulnerabilities in LLVM bytecode, so we want to demonstrate these vulnerabilities on pseudocode. And we map LLVM instructions to pseudocode line numbers. So when we find some vulnerable instruction in an LLVM bytecode, we can locate this vulnerability in pseudocode. So let's discuss vulnerabilities we can detect now. First of all, iOS applications can transfer some sensitive and security-critical information via non-protected connections, and it makes this application vulnerable to man-in-the-middle attack. Most of applications from our research, they communicate with main web server, like banking applications, and this type of vulnerability is very important. For example, application can turn off SSL certificate check. It often happens when developer forget to remove the test code, and we can detect such functions. Also, application can use HTTP protocol to transfer some utility data, for example, maps, news, etc., some information, and this data can be tampered with, and it can help attacker to make a phishing attack or to change some application logic. We detect all constant strings in binary, and so we can find these connections. Apps sometimes use applications sometimes use insecure cryptographic functions like hashing, ciphering, pseudorandom number generators, etc. MD4, MD5, triple DES, whatever. Also, application can use hard-coded encryption key, and the attacker can reverse the application, get this key, and use it for sensitive data disclosure. So we can match these function names and find these vulnerabilities. Every application can gain access to pasteboard, so developers have to turn off its usage, especially for important data. The common error is not to turn off NSLock usage. Information in log can help attacker, and this information can be simply viewed in Xcode if you attach your device to computer and even don't need a jailbreak. Finally, application have to implement a function which describes behavior in background mode. Otherwise, the screenshot will be saved in application directory. This screenshot can contain some sensitive information like credit card numbers, telephone numbers, etc. And information which is stored in application directory can be stolen. Then, in iOS, developers can use reflection. They can call some methods by its names, and this way they can gain access to private API, which is prohibited by Apple and is insecure in some way. Here are some important vulnerabilities that we don't detect now. All the information that is stored in application directory can be stolen. For example, if attacker have physical access to device or this device is jailbroken. Application can store sensitive, unencrypted sensitive information or some security critical information in application directory, in preference files, in some local databases, or in network cache. Important thing here is that insecure data storage is dangerous not only because that it can lead to data leakage, but also that this data can be tampered with, and if this data is important, if, for example, this data defines some application behavior, the attacker can change this behavior. For example, we met across the application which stores its main web server address in preference files. So the attacker can change this address from HTTPS to HTTP and to carry out man-in-the-middle attack. The other example is when application stores the unsuccessful authorization attempts number in preference files, and this application become vulnerable to brute force attack. Poor data validation vulnerabilities is less important for iOS applications than for web application, but it still can be found here. Both poor data validation vulnerabilities and sensitive data leakage can be found by data flow analysis. We must track the sensitive information through data flow. The main problem here is that we must determine which information is sensitive. So how can we tell that this variable contains, for example, passwords. We suggest some heuristics, for example, using, of course, variable names, then data ciphering, then some API functions as sensitive data source, and, for example, some elements of interactive analysis to ask user which information is sensitive. This work is in progress. Then each application which operates some sensitive information shouldn't work on jailbroken device. But the standard algorithm of jailbreak detection can be bypassed. So we can detect this algorithm, implementation of this algorithm in binary code. I think the most important class of vulnerabilities here is authentication vulnerabilities. No two-factor authentication, weak password complexity requirements, and weak control of number of unsuccessful authorization attempts. These vulnerabilities are hard to detect, and usually they should be detected on server side. We have implementation for some server side and for Android applications, and we want to apply these ideas to iOS applications. The main ideas of our approach is the following. We detect the counter, which is responsible for unsuccessful authorization attempts number, and we detect password validation function and fuzz this function to recover its complexity requirements. Here is some piece of demonstration. Here we show some assembly vulnerable snippet. In this snippet, we call vulnerable function that turns off a certificate check. Then we translate this code to LLVM. Here is our call. And finally, we have this call, and we see that the argument is 1. So it's vulnerable in our pseudocode. So we have analysis report, this XML. We see what the source file, the line number, and the vulnerability name. We use this tool for some bunch of applications, and here are some statistics we can show. Of course, these statistics represent the current states of our tool. Of course, we have false positives. As I said, we will enhance our analysis engine, but our tool shows these statistics, and that's it. So we presented our toolset. This toolset can find vulnerabilities in iOS applications only using its iTunes link. And we present these vulnerabilities on human-readable pseudocode. The future work is to enhance analysis, to develop data flow analysis algorithms, taint analysis, etc., to reduce number of false positives, and to make our pseudocode closer to source code, so to develop a decompiler. Thank you for attention. Any questions?
Not a question, just a comment. have you thought about finding in the body of binary API keys, for example, for Amazon or other services? You know, if you have API key, you can use the server. And sometimes some developers, they include not only these keys, they include also private keys for SSL.
Okay.
Yeah, it happens, but we don't detect it automatically yet.
Hi, first, great tool. Do you have any plans on releasing it, the source?
No, unfortunately, it's a proprietary tool.
Okay, and so you showed some statistics on how many apps. Is that statistics based?
A couple of hundreds.
Okay. And then I was just wondering, a lot of apps will introduce full SDKs, so there will be maybe 2 or 3 functions for SSL pin checking or I don't know, other functionalities, obfuscation. Are those things thought about in the tool?
So which functions?
For example, if banking applications will use official SDKs, for example, Gemalto, let's say, and they have functionalities which are in the SDK. So you will have SSL pinning, which is a functionality in the SDK, but it's not because it's in the source or in the binary that the application uses it. You see what I mean?
Not quite, sorry.
Yeah, okay. Well, no problem.
Thank you.